the problem and we already know the theories. So from the Reynolds number you see here, we already know the definition of the Reynolds number, so I'm not going to discuss the definition of the Reynolds number now, but just quickly let's have a review. If the Reynolds number is less than 2300, then we say this is laminar, the flow is laminar. If it is greater than 2300, we can say transitional or turbulent. This is for internal flow. When this is external flow, you know internal flow means flow inside the pipe. External means outside. So for external flow, the critical Reynolds number is 5 into 10 to the power 5. So that means if you calculate the Reynolds number, if you find it is 5 into 10 to the power 5, so then you can say the flow is turbulent. But if your calculated Reynolds number is less than this value, then we will say the flow is laminar. So now we will solve some problems. The basic difference is when it is internal flow, then the Reynolds number, if it is less than 2300, the flow will be laminar. But for external flow, it is 5 into 10 to the power 5. So we have got the first problem here. So let's read the question at first. Consider air flowing over a 2 meter long flat plate. So just consider this is a 2 meter long flat plate. This is the leading edge, this is the trailing edge, okay? The velocity is 3 meter per second and 6 meter per second. So we have got two different velocity. We need to determine the Reynolds number at two different positions. You look here, 0.75 and 2 meter from the leading edge. So this is actually the inlet or the leading edge. You can say this is the outlet. We can say, okay, this is approximately, let's say, the half of the plate, so 1 meter. It is x equal to 0.7. So we need to calculate the Reynolds number at these two distance, these two position. Yeah, and we need to discuss the flow behavior. So whether the flow is laminar or turbulent, right? And the air temperature is given 40 degrees centigrade. So this 40 degree centigrade temperature, this is the air temperature. So we need to calculate the properties. Okay, so let's start with the solution at first. So as I said, my intention is I'll try to make the video as short as possible. So we'll write down a couple of assumptions. So we'll say, okay, this is a steady process, okay? So the all operating conditions we are considering, this is steady, it's not changing with the time. That means especially the air properties or the other properties, so everything we are considering this is constant. So we said the steady operating conditions, and we will say the properties are constant. So properties are not changing. So we said it's 40 degrees centigrade temperature. So our assumption is, okay, it is constant. So now, if you know, guys, the Reynolds number definition. So we know the Reynolds number definition is normally, we can write it down like the velocity, the distance. Here, this is a plate. So this is actually the length L. So you can say the distance. And, the kinematic viscosity. This is called the Greek symbol nu. Nu. It is called the kinematic viscosity. There is other definition for Reynolds number. You can write it is like this. The Reynolds number, when you're talking about the external flow or internal flow, you can write it as density, velocity, diameter, and dynamic viscosity, right? Yes. So this is the two definitions. So here we'll use this first one. So you can ask me why. We know the velocity, we know the distance. So what else we need? We need the kinematic viscosity. So at first, I will write down the solution here, or the analysis here, like this. Reynolds number, it is equal to velocity, distance, and kinematic viscosity. So here we know velocity, we know the distance, but we don't know the kinematic viscosity. So we need to calculate the kinematic viscosity of air at 40 degrees centigrade temperature. So here you see this is the okay, I need to get the table here. So this is actually the properties of air. We have got the temperature is this. So this is the temperature is given. So now what do we need? we need the viscosity, kinematic viscosity. So this is the kinematic viscosity. If we just go this way, so this is the value we need. So the kinematic viscosity at given temperature is 1.702 10 to the power minus 5. So that's the value we need. Right. So yeah, write it down. It is 1.702 and 10 to the power minus 5 meter square per second. So this is the value given. So now we will analyze this total system. We have got two cases, 0.75 and 2 meter, and for two different flow rate, 3 and 6. So if we write at x equal 0.75 meter, and let's say the velocity v equal 3 meter per second, then the Reynolds number, it will be, you see the v, 3 meter per second, x distance 0.75 meter, kinematic viscosity is 1.702 10 to the power minus 5, it is meter square over second. So the value we'll have here is, we can say from the calculator you will get, it is 1.32 10 to the power 5. So see guys, here it is 1.32 10 to the power 5. It is actually less than 5 into 10 to the power 5, the critical Reynolds number value. If the Reynolds number is 5 into 10 to the power 5, you can say it is turbulent. But this value we already got from the calculation is less than that. So you can say, okay, the flow is laminar. Okay, so our conclusion here is flow is laminar. Flow is laminar at this distance. Now we'll check what will happen if x equal 2 meter according to the question here. At 2 meter what it is. So let's check it out. So at 2 meter, when the flow is, okay, initially we got the flow is laminar. Now I'll write down here like this. So the Reynolds number again, Vx nu. So velocity is 3 meter per second, and the distance is now 2 meter instead of 0.75, and it is 1.702 10 to the power minus 5 meter square over second. So we'll get when it is, at 2 meter from the leading edge, so we'll get it is 3.52 10 to the power 5, which is also less than 5 into 10 to the power 5. So that means its flow is laminar here again. So when the velocity is 3 meter per second at both positions, 0.75 and 2 meter from the leading edge, flow is laminar. Now we will check when the velocity or the air, the speed is 6 meter per second from the question. So now write it down here. At 6 meter per second, when x equals 0.75 and v equals 6 meter per second, the Reynolds number, it will be 6 meter per second into 0.75 meter over 1.702 and 10 to the power minus 5 meter square per second. So it will be 2.64 and 10 to the power 5, right? So that means still it is less than 5 and 10 to the power 7. So we can say flow is laminar, isn't it guys? Look here, it is actually less than the critical Reynolds number because this is external flow over a flat plate. But when you look here, the other case, like when x equal 2 meter and velocity equals 6 meter per second, then the Reynolds number, see, it will be this 2 meter 6 meter per second over 1.702 and 10 to the power minus 5 meter square per second. So now we'll get the Reynolds number is 7.05 10 to the power 5, which is clearly greater than the critical Reynolds number 5 and 10 to the power 5. So that means at this position the flow is turbulent. the flow is turbulent. Also quick, so I'll discuss it during the lecture, and you'll get more precise and comprehensive understanding during that time. So that's all.